Hey guys, and welcome to my lecture on Fourier series. As I already explained in the last tutorial, when the signal is periodic in time domain, to go from time to the frequency domain, we need to use Fourier series. Joseph Fourier was the genius French mathematician and physicist who came up with the idea of presenting a periodic signal using a set of oscillating functions. Basically, using Fourier series, you can present a periodic signal xt as a linear combination of complex exponential functions where ck can be found using this integral. The top equation is commonly referred to as Fourier series synthesis equation, and the bottom one is Fourier series analysis equation. Ck is called Fourier series coefficients, and t is the fundamental period of xt. Also, omega naught is the fundamental frequency, which is 2 pi divided by t. Now let's understand why it's valuable to present a periodic signal as a linear combination of complex exponential functions. Let's assume this complex exponential function goes through an LTI system. As we learned from the time domain tutorials, for an LTI system, the output is xt convolved with ht, which is basically this integral. Xt is this complex exponential function. In order to find xt minus tau, we just need to replace t by t minus tau. So here's what we get. Again, I'm replacing t by t minus tau. Now let's break this term into two separate functions. Here we go. This term has nothing to do with tau, so we can bring it out of the integral. Let me write it again. The integral variable is tau. This means after we find this definite integral, tau is gone and the final result is a function of omega naught. To understand what I just said, let's look at this simple example. The integral from 0 to 1, 2t plus a dt. A here is a constant number. From calculus, the solution to this integral is this. 2 by 2 is cancelled and we get t squared plus at. Now to find the final answer for this definite integral, we need to replace t by upper and lower bounds and subtract them. So we get 1 plus a minus 0. As you can see, the final answer is a function of a and the integral variable, i.e. t, is gone. The same story here. The final solution to this integral is a function of omega naught. We usually call this function h, or frequency response. I will make the frequency response crystal clear in the upcoming tutorials, but for now, if you are curious, the frequency response means how the LTI system responds to different frequencies. Yt becomes the frequency response multiplied by e to the power of j omega naught t. Let me erase this stuff and write it one more time. If this complex exponential function with the frequency of omega naught goes through an LTI system, the output is basically the same thing multiplied by the frequency response at omega naught. What does this mean? If this frequency goes through an LTI system, the frequency at the output is not gonna change. So here is the first main conclusion. The LTI system does not change the frequency. For example, if cosine 5t goes through a system and we get cosine 7t as the output, this system is not definitely LTI because the frequency has been changed. Or another example, e to the power of j2t is applied to this system and the output is e to the power of j3t. This is not obviously LTI as the frequencies are different. So keep this in mind, an LTI system does not change the frequency. Now let me look at this interesting property of an LTI system from a different angle. If the input frequency is k omega naught, the output frequency accordingly becomes k omega naught. Again, LTI system does not change the frequency. Also, the complex function is multiplied by frequency response at k omega naught. Now the system is linear. As we learned from the system properties lecture, if we multiply the input by ck, the output is also multiplied by ck. Again, because the system is linear, a linear combination of inputs results in a linear combination of outputs. Now, look at this one carefully to see the absolute beauty of Fourier series. If you can represent a periodic signal, let's say xt, in this form and apply it to an LTI system, the output is basically the same thing, just you need to multiply each complex function by the frequency response at that specific frequency. In fact, to find the output, you don't need to do the convolution in time domain anymore. This is actually the foundation of filtering, which I'm gonna cover in the upcoming tutorials. So, the whole idea behind Fourier series is to represent a periodic function as a linear combination of complex exponential functions, where ck is 1 divided by t multiplied by this integral over one period of xt. These two equations are commonly referred to as Fourier series. To intuitively understand the meaning of these two equations, I'm going to connect the concept to the Rgb color model. RGB stands for red, green, blue. As you may know, each color in the world can be created by mixing three fundamental colors, red, green, and blue, with appropriate weights. For instance, yellow is 1 unit of red plus 1 unit of green plus no blue. Or another example, this color is 1 unit of red plus no green plus 1 unit of blue. Or the orange color is 1 unit of red plus half unit of green plus no blue. Last example, white is 1 unit of red plus 1 unit of green plus 1 unit of blue. So again, each color can be represented as a linear combination of red, green, and blue with the appropriate weight. Here you can see different frequencies as different fundamental colors. Again, frequency as colors and CKs are the weights for each color. Now let's solve some example to practice how to find CKs. First example, this periodic signal is given and the question is, what is CK? The period is clearly 4. So omega naught is 2 pi divided by 4, which is pi divided by 2. To find ck, we need to find this integral. The integral is over one period, so it doesn't really matter if we go from -2 to 2, or -1 to 3, or 0 to 4. As long as we cover one period, that's all good. I personally prefer to choose symmetric interval whenever possible. So in this example, I go from -2 to 2. The function is 0 here, and 1 in this interval. So the integral is non-zero from -1 to 1, and x of t is 1 in this interval. Oh, I forgot dt. As you know from calculus, the integral of e to the power of at is 1 divided by a e to the power of at. This guy is Ra, so the solution to the integral is this, from -1 to 1. Let me bring -1 to the front. To find the final answer to this definite integral, first I need to replace t by the upper bound minus the lower bound. Multiply the minus sign by the parentheses, here's what we get. From my tutorial on complex numbers, we know sine A can be expressed as e to the power of ja minus e to the power of minus ja divided by 2j. Here, k omega naught is a, but 2j is missing at the bottom. So you can write 4j as 2 multiplied by 2j. Then, bring 2j inside the parentheses. Based on this equation, this is sine k omega naught multiplied by this term. So ck is sine k omega naught divided by 2k omega naught. Let's replace omega naught by its actual value, which is pi divided by 2. Here's what we get. 2 is cancelled by 2, and we get this. The problem here is we have k in the denominator, so k cannot be 0, therefore this expression is valid only when k is not 0. What about when k is 0? To answer this question, let's look at the definition of ck again. If we replace k by 0, this term becomes 1. So c0 becomes this. As you know from calculus, this integral means the area under the curve over one period. Let's look at the signal again. The area for this box is the length 2 multiplied by the width 1. So we get 2 for the area. This means c0 is 1 divided by 4 multiplied by 2. 2 is cancelled by 4 and we get 1/2. Here's the final answer. ck is this when k is not 0 and 1/2 when k is 0. Done. Next example. This periodic impulse train is given and the question is what is ck? It's clear that the period is 6. So omega naught is 2 pi divided by 6, which is pi divided by 3. To find ck, we need to find this integral. Again, as long as we cover one period, we are good. I prefer to have a symmetric interval. That's why I go from -3 to 3. During this interval, xt is just a delta function at the origin. So let's replace it here. Delta t is non-zero only at the origin. So based on shifting property, which I already covered in the elementary signals lecture, to find the integral, we just need to replace t by 0. The integral is equal to 1 and ck becomes 1 divided by 6. Last example. This periodic signal is given and our mission is to find ck. The period is 2, so omega naught is 2 pi divided by 2, which is pi. To find ck, we need to find this integral over one period. To have a symmetric interval, I go from -1 to 1. The signal is -1 in this interval and 1 in this interval. So we need to break this integral into two integrals. One from -1 to 0, where the signal is -1, plus another integral from 0 to 1, where the signal is 1. From calculus, we know the integral of e to the power of at is 1 divided by a eat. This is our a here and here. So the first integral becomes this from -1 to 0. And the second integral becomes this from 0 to 1. Let's simplify them. Minus is cancelled by minus, and I'm going to replace t by upper and lower bounds. Here we go. The same thing for the second term. This term is common, so we can factor it out. Also, this is 1 and this is 1. So by factoring the common term, we get this. Also multiply the parentheses by the negative sign. Let's write it again. 1 plus 1 is 2. From my lecture on complex numbers, we know cosine A is e to the power of ja plus e to the power of minus ja divided by 2. This is the a here. To create the positive sign, let's factor -1. Also, 2 is missing in the denominator, so let's divide this by 2 and multiply it by 2. It's basically the same thing. 2 can be cancelled by 2. Now you can replace this by cosine k omega naught. Let me write it again. 2 is the common term, so we can factor it out and cancel it by the 2 in the denominator. Also, let's replace omega naught by its actual value, pi. So here's what we get. The problem is we have k at the bottom, so this expression is valid only when k is not 0. As I explained in the first example, c0 is equal to this. The integral means the area under the curve over one period. Let's look at the signal again. Over one period, this area is 1. but it's below the x-axis, so the area becomes -1. Also, the area here is 1. Therefore, the total area is -1 plus 1, which is 0. So here's the final answer. Ck is this when k is not 0, and it's 0 when k is 0. Done. Last thing that I want to cover in this tutorial is some interesting properties that Ck inherits when the signal in the time domain is even or odd or real. Before I get into details, let me refresh your memory. As we saw in the signal properties lecture, an even signal is symmetric around the y-axis. An odd signal is symmetric around the origin. Also, based on Cartesian representation that we discussed in the complex numbers lecture, each signal can have a real part plus imaginary part. If the imaginary part is 0, the signal is called real. For instance, sin t is a real signal as there is no imaginary part. Here is another real signal. But this signal is pure imaginary as the real part is 0. Last example. This signal has both real and imaginary parts. Now let's continue. I'm going to consider even, odd, and real signals in the time domain and show you the shape for Ck. Again, my main objective in this section is to explain what properties Ck inherits when xt is even, odd, or real. Let me write them down first and then I will prove them. If xt is even, Ck is even. Based on my lecture on signal properties, this means Ck is equal to C minus k, or we can say Ck is symmetric around the y-axis. If xt is odd, Ck is odd, which means Ck is equal to minus C minus k. If xt is real, Ck is equal to C minus k conjugate. As you may remember, the conjugate is used to switch the sign for the imaginary part. For example, by applying the conjugate to 1 plus j, we get 1 minus j. As you can see, we just switch the sign for the imaginary part. Another example, the conjugate of 2j is minus 2j. As you can guess, the conjugate has no impact on the real number. To apply conjugate to a complex exponential function, we need to switch the power sign. This is basically the same as switching the sign for the imaginary part. Let me prove it. Based on the Euler's formula that I covered in the complex numbers lecture, e to the power of jt is equal to cosine t plus j sine t. To apply conjugate here, we just need to switch the sign for the imaginary part. Also, based on the Euler's formula, you can write this as cosine minus t plus j sine minus t. From trigonometry, we know this is cosine t and this is minus sine t. So we get this. The conclusion is these two are equal. Again, to apply conjugate to a complex exponential, just switch the power sign. Okay, let me erase these examples and continue. If xt is even and real, Ck is real, which means the imaginary part is 0. If xt is odd and real, Ck is pure imaginary, which means the real part is 0. The proof for all these statements is super easy, so please don't memorize them. I'm gonna prove number 1, 3, and 4. Your assignment is to prove 2 and 5 to practice. Let's start with the first statement. If xt is even, Ck is even. From signal properties lecture, we know when the signal is even, xt is equal to x minus t. Now we want to prove for this signal Ck is also even, i.e. Ck is equal to C minus k. To prove that, let's start from the Fourier series equation. Let's replace t by minus t. Here's what we get. Now let's replace minus k by p, which basically means k is equal to minus p. When you change the variable, you also need to change the lower and upper bounds in the sigma. When k is minus infinity, p is minus infinity, so p becomes plus infinity. When k is plus infinity, p is minus infinity. By replacing all this stuff here, we get this. As you can see, the sigma is from plus infinity to minus infinity. The thing is, sigma from a to b is exactly equal to the sigma from b to a. It doesn't really matter if we say 1 plus 2 plus 3 or we say 3 plus 2 plus 1. The result is the same. So let's switch the upper bound with the lower bound. Now p is just a name. You can call it whatever you want. I'm gonna change the name to k. Here's what we get. Let me write xt again. Now we know the signal is even, which means x minus t is equal to xt. The left sides are equal. This means the right sides must be equal. We have the same exponential functions and the same sigmas. This means these two are equal. Here's the conclusion. ck must be equal to c minus k, or we can say ck is even. Here is the next statement that I want to prove. If xt is real, ck is equal to c minus k conjugate. When the signal is real, it means xt is equal to xt conjugate, or we can say conjugate has no impact on the real signal. For instance, 2 is equal to 2 conjugate. To prove this statement, let's start with the definition again. Now let's apply conjugate to both sides. Here's what we get. As I already mentioned, to apply conjugate to a complex exponential function, you just need to switch the power sign. Based on the previous example, if we replace minus k by p, we get this. Again, p is just a name, so I'm gonna replace it with k. Here we go. We know the signal is real, which means xt is equal to xt conjugate. The left sides are equal. This means the right sides must be equal. The exponential functions are the same, also the sigmas are the same. So these terms must be equal. The conclusion is ck is equal to c minus k conjugate. The last statement that I want to prove is if xt is even and real, ck is real. From the first statement, we know if xt is even, ck is even. Also, from the third statement, we know if the signal is real, ck is equal to c minus k conjugate. The left sides are equal. This means the right sides must be equal, i.e., c minus k is equal to c minus k conjugate. Let's replace minus k by k. Here's what we get. This means conjugate has no impact on ck, or we can say ck is real. For instance, here the conjugate has no impact on the number as it's real and the imaginary part is 0. Before I let you go, let me solve one example. ck is given and the question is if the signal in time domain is even, odd, or real. To answer this question, first we need to find c minus k, or we need to replace all k's by minus k. Here we go. From trigonometry, we know cosine minus theta is equal to cosine theta, and sine minus theta is equal to minus sine theta. So c minus k becomes this. Bring the minus sign to the front. If you compare ck by c minus k, you can see the difference is in the minus sign. Or we can say ck is equal to minus c minus k. Therefore, the signal in time domain is odd. To see if the signal is real or not, you need to find c minus k conjugate. To do so, we need to apply conjugate to c minus k, which means switching the sign for the imaginary part. Here's what we get. If you compare these two terms, you can conclude that they are equal. Therefore, the signal is real in the time domain. Okay, that was my lecture on Fourier series. Thank you so much for your time. If something is not clear, please type your question in the comments section. I will do my best to respond ASAP. Also, please don't forget to subscribe to my channel to make sure that you are not missing any new video. Thanks again and see you guys in the next tutorial.